Hi, I'm Dean Bushmiller with Expanding Security, and this is Network Collection Tools and Techniques. Use or consumption of this material by AI is expressly forbidden. Let's get started. When we look at network collection, what are we talking about here? We're probably talking about packet sniffing here. That's really what we're getting into. So if we look at this collection, like, why do we do it? What's the whole point to this? Well, it supports detection efforts and incident response. Those are the two things. And it may also support forensics. You have to ask yourself, what's our mission and why should we capture? In a lot of cases, you leave this to other tools or you leave this to other vendors that are out there, but you have to know why you're doing this capturing, because this is going to be an expensive proposition for the organization to involve themselves in incident response at the packet level. Whatever answers you come up with, they're going to drive the placement of your tools, the accuracy, fidelity, maybe even say granularity of the capturing that you're doing, and how you actually do your retention. When we look at collection out there, what is that? What's involved in that? Well, that's monitoring and capturing all the packets passing through a particular network segment. And that's important to talk about network segments here. That's your first core concept. The tool that you will use generally is a software sniffer. That software sniffer, it understands that each individual host that we have on our network listens for the broadcast address and its MAC address as the destination, and that looks like all Fs, yeah, okay? Now we can reconfigure that network card into promiscuous mode if the operating system allows us to do that. These are specially designed operating systems in a lot of cases. You can run Wireshark on your particular device and do packet captures there, but a lot of times what will happen is it'll only capture the packets internal to your machine. If you're running this on a Windows machine, it probably won't allow you to do this at all. Now, once we've got that software sniffer running, now we have to tune all of this stuff. This granularity of tuning, how are we going to adjust this? Because this could be huge amounts of data. We do that on a per link choice. We look at the critical services. Maybe we turn up the listening and capture all of the packets. We look at the internet facing. Hey, we won't capture this stuff that's going on the inside, on the outside of the firewall. We'll capture everything going on the inside. You might do both, by the way. Or we have an end user client that's misbehaving and we want to figure out what's going on. So we'll listen in on that device and see who it talks to. This could also give us indicators of compromise. There is an acquisition granularity that goes in here. And that is based on those devices that we're choosing. On those per links, we could do full packet capture, which is really expensive. We could do something called snap length, which is typically the header. They say it's the first 64 bytes, but you could arbitrarily make that any size that you want to. Generally, what we're doing is if we're doing the snap length, we're capturing all of the header information that's important to us and a little bit of the starting data information. We might go into that area to see that, oh, we can do an MD5 hash of the type of file that's supposed to be being transmitted at that point, but not the actual file, because again, that would be the entire session collecting all of the data, and then now we're back to full packet captures. We could do flow records. If I go from here to here on the network, I capture that flow going back and forth. And we could also do protocol metadata, which is the percentages of communications of what kinds of protocols that we're talking. This is less granular as we go along, so therefore we won't have as much evidence to go ahead and say, I know exactly what happened there, because we're getting a vaguer and vaguer picture. Next is location. Well, wait a minute, Dean, isn't that the client? No, because we might have remote communication with a small office, home office. We might do this at the central office, or we might have some cloud infrastructure. So in all those cases, we've got some knobs to tune and some decisions to make. And that goes back to what is our main purpose here? And then that's going to drive all of these things here. Next, we do the analysis on these particular devices, and that's done with Wireshark. It's really good at display filters, and it's really good at following the streams. There are other tools that actually do this, but it's really good at this, and most people understand how this tool works. Now, I know that the purists out there are saying, oh, well, we're going to go ahead and look at it on the command line with TCP dump. But I start getting a headache after about 2 or 3 hours of doing that. Next, we look at our architecture for network collection. Remember that I would say all networks are fully switched, but there's that little caveat in there. Some people have hubs still connected out there. Remember, a fully switched network has many ports, but each port is one broadcast domain, and that's important for our tapping. The switch is going to create a layer 2 to layer 2 virtual direct connection between these two devices. It's not a fixed direct connection, but it's a virtual direct connection to reduce the overall overhead on the switching infrastructure. Now, we need to capture that direct connection for inspection. That's the first piece in our architecture here. So how do we insert ourselves, our listening devices? What are our listening devices to get inside of that connection that we've created there? And that comes in 2 flavors generally. That's either span or tap. Span is a switch configuration. We go to the actual managed switch. If it's a managed switch, if it's an unmanaged switch, you don't have these activities. You go into that switch configuration and you say, mirror all the traffic from this source to this destination through this port right here. And I'm going to show you at the end of this section, I'm going to show you a little kind of physical diagram of how that all works with a little bit of show and tell. But that span port switch configuration can drop packets. It is possible. It can reorder packets, and it can corrupt timing analysis. Now, if you're doing only incident response, this may be good enough for you. But if you're going to the forensic level, you cannot do this, because forensically, you won't be able to present this in a court of law and prove that there weren't packets dropped. Okay, so what do? Well, that's where we bring in a tap, which is a physical device. That's going to require separate networking to communicate back to our collection station and separate processing of all those packets. Now, here's the most basic tap that you can find on the market today. I think this is like $200. This would mean that we would go to the switching infrastructure and we would say, okay, we're going from source to destination, and we're going to actually break the connection on the switch, pull the wire out and plug it in here, and then pull another wire out and plug it back into the switching infrastructure. So the switch is no longer a part of this. On the back side that you can't see here for this is it's got a connector that goes out and goes to a particular set of storage. Some of the more sophisticated devices, we don't have to run a network connection back to another location. What we can do is we can just plug in at this location and actually plug in like a USB drive if we want to. How are we going to store all this data? Speaking of USB drives, well, now we got a problem. Because think about all the file transfers that you did in a day and how much data there was just in the files that were copied to your machine. Then add in all the internet connections and all the overhead for the networking processes that are going on, like a DHCP and pinging back and forth, ICMP. All of that stuff that's going on behind the scenes is now all being captured if you're doing full packet captures. So you might need an array like this. In the enterprise, it's not uncommon for us to have, and I think this is about like a 50 drive array. I didn't actually do the math on this, but if I were to purchase a drive at this point, let's say it was a 17 terabyte drive, and I were to put it in here, I would be consuming a petabyte of drive space inside of here. And that is possible in the network. You have to be thinking about long-term storage of this data as well as short-term for your inspection. I'll explain that in the forensics section later on. Now we run into another problem. Most of the traffic that's being passed back and forth today is encrypted with TLS. So you say, well, Dean, I want to view that encrypted traffic. Okay, that's fine. That means that you need to terminate the connection with a proxy, do the inspection on that traffic for whatever you're looking for, maybe even pulling and capturing those packets, and then rebuild the connection with the proxy so that when I go to buy something on Amazon, for instance, it sets up the TLS connection between me and that server. What you're doing is you're inserting yourself in the middle and inspecting what's going on. Let's go back to the beginning here. Start from the mission. We look at our visible network architecture and how much transmission we're going to do. We're going to make sure that all of the IP addressing that we're using is pre-NAT source IP addresses, because if it's NATed and it says 192.168.1.1 and we've got a bunch of different clients that are coming in over the same IP address, we're not going to understand what's going on. We need to place our tap, or we may even do span because it may be reasonable for us in a hurry to collect data like that. And then we need to size our storage. But see, that's not the big thing here. You are the big thing. You are the best tool in all of this if you want to go to the level of doing this kind of investigation, this incident handling, and this forensics. What that's going to require is packet analysis skills. You can't just rely on the machine to do this. You have to look at the weird things that are happening. That's your job. Protocol understanding is also required here. Now, in this next section, what I'm going to do is I'm going to do a little show and tell. It's going to be a little bit different. And then after that, we'll get into the AI section. Normally, you see me here in the window. But today, we're going to look down here. I wanted to give you a diagram of physically what's going on when we're doing packet capturing. Our goal is to figure out what the exact communication on a packet level is between this client and this server. We've got a wired communication between them that's going to some sort of switching mechanism. We don't want to disturb this client or this server, so what we do is we reconfigure this switch. Now, the way that we do that is we use something called span port. We will pick a particular port off of this switch and say, mirror the traffic from here and from here through this particular port. It could be multiple ports, but in this case, we'll keep it simple and we'll just mirror one port. We do that through the configuration of the actual switch itself. Now, we still need a place to capture information, and that's where we bring in what's called the listener. This is just another computer on the network doing packet capturing. So once we connect in to this particular switch right here, now we can listen, pull all those packets because the switch is giving us that data. We turn this particular network interface into promiscuous mode. This is the best way to do this in the enterprise. We will also need something else. And in this case, because this is such a small host, we're probably going to need to connect up some sort of long-term storage to this, some sort of very large storage. This could be a storage area network, but it needs to be in proximity to this listener right here. Once we've done that, we can capture all of our packets. There is another way to do this. This does interrupt the actual client when we're working with this particular technology, but we can still get it done. So what we can say is, okay, here's my listener. We're going to connect that listener into what's called a tap. This can be passive or active. At this point, what we do is we disconnect the client from the switch, disrupting the communication. We usually connect into the exact same port that they were communicating on so that we don't have any problems whatsoever with renegotiation. And then we connect that client into this tap. It's the exact same communication path. We've just interrupted it and given ourselves a way to communicate. So if we can't convince this switch to change because it may be an unmanaged switch, we can do this with another device in the way, but it is going to interrupt the signal. So that's how you physically get communication packets passed to a listening device. How is AI changing network collection? Well, it's helping us to reduce our overall overhead. Let's look at current collection processes that are out there. So we capture and store massive raw packets. We don't know when we're going to need these again, so we need to capture it all and let God sort it out later on. Then what we have to do is we also have to write thousands of rigid regex expressions that will allow us to find threats, the needle in the haystack. This is resource intensive. So AI comes along and says, okay, well, what we can do is we can do inline data compression, not compressing the packets themselves. I'll explain this in a second. Behavior-based engine analysis, and automated forensics assistant, if we put all these things in place. So let's look at these transformational areas. Smart triggered forensics capture. What's that mean? Well, machine learning is really good at taking large quantities of information and saying, this is the norm here. This is outside the norm. So if I see the norm, okay, fine. I've learned that this is the norm and that's anomalous. But it's not just anomalous one time. What it can do for us is it can say, okay, there's a lot of background noise going on here that we've seen many times before, and we don't have to capture that anymore. It'll also allow us to do predictively looking for micro anomalies. Let's say that you and I ping each other every day one time. We do ICMP back and forth. And that's a normal process that we do. What happens if inside of that ICMP packet, instead of putting the regular data that we transmit, which is basically the character strings for ASCII in there, it starts being, something else, like I'm sending secret messages in there. It can look at and spot these micro anomalies much more readily than end users can. What this will also do is programmatically capture targeted PCAPs. So if normally when you and I communicate and we ping back and forth, it doesn't capture that because it says ICMP traffic isn't important to us if it's internal. ICMP traffic going externally, okay, well that's important, so I'll log that stuff over there, I'll capture that stuff. But something's going on here, and normally it would track the ICMP traffic, but now the shape and size of that ICMP data that's inside of there is different. Okay, I want to capture everything at this point. I want full packet captures. So it can programmatically increase the quantity of data so that we can then do an analysis later on. That's just amazing to me. That will be a huge data savings area within our network if we tune well and we have the right tools. Now we can also look at behavior replacement of signatures. So like I said, those thousands of regexes that we want to put out there, we don't need to do those anymore because we don't need those rigid signature lists that are out there. What we can do is we can mathematically map a particular device's behavior, detect those small shifts that are happening, and this is really key, over long periods of time. The techniques here are parsing the normalized metadata streams, doing a real-time analysis, constructing the active baseline, which would include the normal transfer data from every host, every server, and every user. We don't think in those terms as network monitoring people. We just say, okay, we've got a problem over here. Let's go ahead and look at what's going on. Let's do the investigation. Did we capture all the information so we can do this information? That's not what the AI is doing. It's looking at all of these relationships because remember, large language models can look at large quantities of data. Think about millions of different kinds of connections is the way that these models work better. Last one is AI-guided telemetry and queries. We can now do natural language queries against a lot of this data when we can articulate it as a person, but we can't say it in packet speak because we don't have the right regex in our mind. We can look at the historical flow of data and scaling and make sure that we can actually get that done. The technique here is trained on the telemetry schemas and trained on the network mapping. So that's how AI is changing network collection tools and techniques.